fifth video in Chapter 4, Newton's Laws of Motion, and it's going to deal with Newton's second law, primarily with using Newton's second law to solve problems. First off, Newton's second law says that the net force acting on an object is equal to the mass of that object times the acceleration that results from the force. I want to go back to Newton's first law. Newton's first law says, basically, that if a net force is acting on an object, it will accelerate. And if there is no net force, if there's no force at all, or if the force is add to zero, then there's no acceleration. So the first law says forces cause acceleration, and the second law sort of quantifies it and gives us an equation to use. So the net force is equal to the mass of the object times the acceleration that the object will gain because of the force that's acting. A better way to look at this to really feel the relationship is A is F over M, and I'm going to even write it in using a fraction bar that's horizontal, so we can really see this. So all I did was multiply both sides by M, right? I'm sorry, divide both sides by M. So I got A by itself and then F net over M. Acceleration is force over mass. Notice acceleration is directly proportional to the force. So a larger force will cause a larger acceleration, and it is inversely proportional to the mass. So if this force acts on a big mass, it'll cause a small acceleration, but if this force acts on a small mass, it'll cause a larger acceleration. Going back to the problem that we worked out, not the problem, but the thing we discussed, I guess, with the bug and the windshield, and it's difficult to grasp that as this windshield hits this bug and the bug hits the windshield, they will exert a force on each other, and the force is the same. Because what we see happen is very, very different. The windshield is basically not affected, and the bug is well, it's affected a lot. Its shape changes, blood and guts everywhere. So we see a different result of this force. But what's different is not the amount of the force, it's the amount of the acceleration. Because if you have this force acting on a little tiny mass, then that'll give you a really big acceleration. But if you have this force acting on a really big mass, then you get a really tiny acceleration, to the point where the acceleration the car feels is negligible, and the acceleration the bug feels is very, very large. All right, so let's talk about a few things before we leave this slide. The direction of the force and acceleration are always the same. So if you have a net force acting, let's say here's an object and there's a force 1 acting to the right and a smaller force 2 acting to the left, so that the net force is a rightward force that looks something like that. The acceleration will also be in this direction. The acceleration is always in the direction of, let me put net down there, the net force, always the same direction. Now, acceleration and velocity are not necessarily the same, but if the acceleration and the velocity are the same, then the speed will increase. If acceleration and velocity opposite, then the speed will decrease. An example of this would be if you're driving down the road and your velocity is in this direction. If you're going at a constant velocity, then the forces pushing the car forward and the retarding forces on the car are equal. So at a constant velocity, F net would be 0. If you want your car to speed up, then you're going to have to increase the forward forces against those forces so that F net does not equal 0 and is in the positive direction. Well, if the net force is in the positive direction, you're going to get an acceleration, and the acceleration will also be in that positive direction, and you'll go faster and faster. But if you want your car to slow down, then what you do is you decrease those forward forces, lift your foot off the accelerator, and so those retarding forces, the ones that would make you slow down, are the bigger one, and so you get an F net in the other direction, and you get an acceleration that's also in the other direction. Well, if your velocity is in a positive direction, and your force and therefore your acceleration are in a negative direction, then your car is going to slow down. So force and acceleration always the same direction. Acceleration and velocity sometimes in the same direction, sometimes in the opposite directions. If they're the same direction, you get an increase in speed. If they're in opposite directions, you get a decrease in speed. And a little reminder about a Newton. Remember the SI unit of force is the Newton. And 1 Newton equals 1 kilogram meter per second squared. Notice this is a mass unit, and this is an acceleration unit. F equals ma. And so the Newton, the unit of force, comes from multiplying a mass unit by an acceleration unit. So a Newton is equal to a kilogram meter per second squared. So if F equals ma, and our acceleration is gravitational acceleration, then the force becomes mg. And this is the gravitational force. That's not the gravitational acceleration multiplied there, it's a subscript. The gravitational force is equal to mg, and we call the gravitational force weight. So if I need to calculate the weight of an object, I just multiply its mass by the gravitational acceleration. A force equals a mass times an acceleration. We have a specific acceleration due to gravity. The force due to gravity is weight. Okay? W equals mg. Now, weight is a force. Weight has units of newtons, not pounds. In this class, every weight will have a unit of newtons. On the other hand, mass, which is similar but a very different thing, mass will have units of kilograms. Mass is a fundamental characteristic of an object. The mass of the object is the same no matter where it is. So if I have an object that's 10 kilograms on the Earth and I take that object up to the moon, it's 10 kilograms on the moon. So the mass is a fundamental characteristic. Weight is the gravitational force acting. So weight can vary. If I take an object that is 10 newtons on the Earth and I take that object up to the moon, it's only going to have a weight of about 1.6 newtons on the Earth. So weight depends on where you are. It's a measure of the gravitational force. Weight is in newtons, mass is in kilograms. So if I need the weight of an object, an example. I have a 10 kilogram object, and I want to know its weight. Weight equals mg. Weight would be 10 kilograms times 9.8 meters per second squared equals 98 newtons. And if I have an object, if I know that the weight equals 200 newtons, and I want to know the mass, then if weight equals mg, then mass must be equal to weight divided by g. So that's going to be 200 newtons divided, okay, I'm going to use 10 for g here, 10 meters per second squared, and 10 goes into 200, 20 kilograms, about, because we used not quite 9.8 for g, okay? It's very important that you know the difference. And if I give you a weight, you need to be able to find a mass. And if I give you a mass, you need to be able to find a weight. Notice the units. If it's in kilograms, it is not a weight. If it's in newtons, it is not a mass. In a problem, you'll be told you have a 40 Newton object or a 3 kilogram object, and you have to know from that, is that M or is that mg? If it's newtons, they've already given you mg. If it's kilograms, that's just the mass. Okay, so be aware of that. Pay really close attention to that. In solving problems using Newton's second law, there are some steps that you need to follow. Draw a diagram of the situation. That's just a sketch. It's not necessarily a free body diagram. It's some of the things you've seen me draw. You know, I have a car and it's driving down the road with a certain velocity. It just kind of helps you get the situation in your head. So just a sketch. Select your object. We work with one object at a time. So with the bug in the car, we would either do the bug or we would do the car. We wouldn't do both. We don't work with systems when we're analyzing forces. We work with a single object. That's usually going to be selected for you in the problem. Identify all the forces that are acting on the object. And just to help you with that, are there any ropes or strings? Then you must have attention. Is anything touching your object? Well, if it is, it might be exerting a force, and it would be a contact force. So ask yourself, is it moving against a surface? Is there friction? Is it resting on a surface? Is there a normal force? Is there a pushing force or a pulling force? You know, those that we sometimes call FA for F applied. Is a box being shoved across the floor? Is there any air resistance? Is an object falling? Is there air resistance that we need to consider? And almost all the time, there will be gravity. Okay? So go through kind of this list. If you're looking at your object and you don't know what forces are acting, ask yourself these questions. After you kind of have your situation sketched and you know what forces are acting, draw your free body diagram. Now, this is not some loosey-goosey diagram. This is your free body diagram. And the arrows should represent the length of the force. And so if you're told that you have an object and it's falling and it's still accelerating, then you know your air resistance arrow must be smaller than your weight arrow. And make your free body diagram work for you. Pay careful attention to the length and the directions that your arrows are in. Then write Newton's second law, and it's that simple. Write F net equals ma. Write it down. F net equals ma. Replace the left-hand side with whatever forces are acting. I'll just use this example. I would replace the left-hand side with air resistance is up, so I would say air resistance, and weight is down, so that's negative, so minus mg. That's the F net, it's the sum of my forces. So replace the symbol F net with the actual sum of the forces that are acting. And then equals ma. So that tells me that the air resistance that object is experiencing minus the weight of that object equals the product of the mass and acceleration of that object. You have an equation now, and the last step is to solve it. Just a little word here, 2 dimensions. We have up, down, and side to side, vertical and horizontal. You have to deal with them separately. Now in this chapter, that'll be easy because things will be acting usually along a line, horizontally or up and down vertically. In the next chapter, we will deal with, I have a box and it's being pulled with a force at a 10-degree angle. And so that force has components, which we will learn how to find in the next chapter. And we have to break it up into a vertical part and a horizontal part. In this chapter, things will either be up and down or they'll be side to side. You will have a vertical acceleration or you will have a horizontal acceleration. You won't have both and you won't have anything at an angle. Okay, but be aware that you have to deal with them separately. So this little symbol, it means F net. So in your notes, you could write F net or F, how would that be best written? Hold on a second. You can say Fx net and Fy net. Net means the sum of, that is the capital Greek letter sigma, and if you've had, I know if you've had calculus, you've seen it, and probably if you've had some other, like Math 3, you've probably seen it too. That just means the sum of. So F net and the sum of F both mean the same thing, okay? But you have to deal with horizontal or vertical. You can't do them both together. Let's start doing equilibrium, the case of a problem in equilibrium. Well, how do you know it's an equilibrium? There are some little key words you need to look for. If you read in your problem that something is traveling with a constant velocity, then your little brain should say, oh, constant velocity, there's no acceleration, and therefore there is no net force, okay? These 3 things, if you see one of them, any one of them, your brain should go, ding, 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 constant velocity, net force is 0, acceleration is 0. So that's how you know it's an equilibrium. In the problem, if you see the words constant velocity, terminal velocity is a constant velocity, or if they say there's no acceleration, or if they say the net force is 0, any of those 3 things, you know it's an equilibrium. And so in equilibrium, F net, well, it says so right there. I was just about to write that. F net equals ma. That means F net and acceleration are 0. Okay, let's work on a problem. A 5-kilogram object is being pulled across the table, and I totally meant to type in there, let me give myself some room, with a constant velocity, because that's why this problem belonged on this page. So a 5-kilogram object is being pulled across the table with a constant, C-O-N-S-T-A-N-T, velocity by a 50 Newton force. What is the force of friction? Okay, we're going to work the problem out, and then we're going to kind of use the shortcut method. I'm going to put up here, how do we know it's an equilibrium? Constant velocity. A equals 0, F net equals 0. So we'll maintain that. Okay, so diagram the situation. Here's a table, here's an object, and it's being pulled. That was supposed to be an arrow. There we go. Pulled to the right is a 50 Newton force. Diagram of my situation. What are the forces? Well, there's a pulling force, and the problem mentions friction, so I know there's a frictional force. There's weight and the normal force, so let's draw a free body diagram. There's our weight and our normal force. Here's our applied force, or the pulling force. You can put a P there if you want to. And there's the frictional force. So that's my free body diagram, and everything's labeled. Make sure all your forces are labeled. Now, we can ignore the normal force and the weight now. I want to put them on free body diagrams, but like I said, we either deal vertically or we do deal horizontally. This object's on a table. It's not accelerating up or down. It's not flying through the air. It's not falling through the table. So the horizontal dimension is the one that we're working with. So we're going to ignore the vertical stuff. I said write F net equals MA, right? And the next step was replace the symbol F net with the actual net forces. That'll be the applied force minus the frictional force. Okay, net means add them up, but I just put a minus sign. That's because the friction's heading in the left direction, and so it's negative. So this is a negative force, and this is a positive force. Equals MA. And now I have an equation that I can solve for the force of friction. It's being pulled across the table with a constant velocity. How is that helpful in this problem? It's helpful because it tells you acceleration is 0. So when I get to this point in my problem, I can, solving for my frictional force, do a little algebra here. Frictional force is equal to the applied force minus MA. Okay, how did I do that? I moved this over here because it's negative and I wanted it positive, and so I get a positive F, and then I subtracted MA from both sides. But acceleration is 0, so what does that leave me? The frictional force equals the applied force. Well, in this case, the applied force is 50 newtons. Done, 50 newtons. Okay? So that was working it out, showing every step. But it's very important that you see what this result is and what it means. If you have an object being pulled with a constant velocity, then the two forces that are opposing each other have to be equal and opposite because it's in equilibrium. So if I tell you a 50 Newton force is pulling an object at a constant velocity, then the opposing force must also be equal to 50 newtons. Okay? You could totally answer that question without having to do any of this work. A 20 kilogram object is falling at terminal velocity, that is a constant velocity. How much air resistance is it experiencing? Well, I'm going to draw a quick free body diagram. I have a weight acting downward, and I have air resistance acting upward. And since I know it's a terminal velocity, I made those the same size. Constant velocity should tell you that acceleration is 0, F net is 0, and that tells me these two things have to be equal and opposite. So the air resistance must be equal to the weight. And, okay, is this the weight? No, it's not. That's the mass. That's the M, not the mg. So air resistance must be 20 kilograms. I'm going to cheat again and use 10 meters per second squared for g because I can multiply without a calculator. 20 times 10 is 200 newtons. Okay? So in the special case of equilibrium, opposite forces must be equal so that you get no acceleration. An object is falling, its mass is 10 kilograms, and the air resistance is 70 newtons. Find the acceleration. Here's our object. There's the weight. Here's our air resistance. And the air resistance is 70 newtons. Let's do Newton's second law. F net equals ma. Replace F net with the actual forces, right? Air resistance is upward, weight is downward. Okay, so this is F net, and there's MA. I've just rewritten the equation. Now we have an equation we can solve. Air resistance is 70. mg, well, the mass is 10 kilograms. And I'm going to take the easy route, and I'm going to make g be 10 meters per second squared. Again, because I can do it in my head. And the mass is 10 kilograms, and I'm looking for acceleration. So that's going to be 70 minus 100 equals 10a. And 70 minus 100 is negative 30. Divided by 10 equals a. A is negative 3 meters per second squared. So let's think about that negative for a minute. What does that mean? Well, we defined in this problem up is positive and down is negative. So we did it right here. Air resistance is up and it's positive. Weight is down and it's negative. So that simply means it's accelerating downward at a value much less than gravitational acceleration. So the air resistance is pretty large and it's approaching terminal velocity, but it's still accelerating downward at 3 meters per second squared. An object is being pushed to the right with a force of 50 newtons. The mass of the object is 5 kilograms. 5, and if the object has an acceleration of 6 meters per second squared, find the frictional force. So I know there's a frictional force. It's accelerating positively, so I draw that arrow smaller than that one. And I need to stick a normal force in there to make it a correct free body diagram. Write Newton's second law. Replace F net with the forces. This is positive, this is negative. So 50 newtons minus the frictional force equals, and the mass is 5 kilograms, and the acceleration is 6 meters per second squared. That's ma. So 50 minus F equals 30. And I'm going to move my F over there, and I'm going to move my 30 over there, and so it's going to give me 50 minus 30 equals the frictional force, and the frictional force must be 20 newtons. Okay. If you were on an elevator and you're standing on a bathroom scale, how would the scale reading change during the trip? And the scale reading in physics, that's your normal force. Okay, that's if you're standing on a scale, it's the scale's force up that it reads, and that's the normal force acting on you. So if you're moving upward, speeding up, well, let's look at how the Newton's second law would help us solve this problem. F net equals ma. I just wrote Newton's second law. And I filled in, replaced F net with the two forces that are acting. So here you are on the elevator. You have a normal force up, and you have the gravitational force down, right? So this is the two forces equals ma. Now, it's the normal force, it's the scale reading that we're curious about, so I solved for that. I moved, added that to both sides. So the normal force equals your mass times your acceleration plus your weight, your mass times gravitational acceleration. So I want to see how this normal force compares to your weight. If you're moving upward and you're speeding up, that means you have a positive acceleration. So what's going to happen in this case is Fn equals a positive ma plus mg. This is a positive number, and so this number is going to be bigger than your weight. So if you're moving upward and speeding up, then you see your weight on the scale get higher. Have you ever been in an elevator and when it begins moving upward, you kind of feel a little heavier? You might feel your knees buckle a little bit. That's because the force that's acting on you is your weight plus the force that's accelerating you upward. So the scale reading would be bigger than your weight. What if you're moving upward and slowing down? Well, let's look at that equation again. If you're moving upward, but you're slowing down, that means you're going to have a negative acceleration. So this term becomes negative. Now that means the normal force is going to be less than your weight. Here's your weight. If you have a negative acceleration, then the normal force is your weight minus ma. And so if you're moving upward and you're slowing down, that scale reading is going to be lower than your weight. If you're moving down, that would be a negative velocity. Speed increasing, that would be a negative acceleration. This problem works just like the last one. The normal force equals ma plus mg. But if a is negative, then this term becomes a negative ma plus mg. So the normal force, if you are speeding up, moving down, the normal force is less than your weight. And so that scale reading would be lower than your actual rate. And moving down, slowing, well, that's a negative velocity, but if you're slowing down, the acceleration would be opposite your velocity, and so it would be positive. So the normal force, again, in this case, would be ma, this being a positive term, plus mg. So when you get to the ending, if you're taking a ride in the elevator moving down, and you get close to the end and you slow, you start to feel heavier, and the scale reading would be bigger than your actual weight. We're actually going to do a lab where you're going to get on an elevator and do all this, so you'll be able to watch that scale reading go up and down. So let's work a problem. A person is standing on a scale on an elevator that is accelerating upward at 2 meters per second squared. Find the scale reading. Okay, I'm going to do it right and not skip any steps. F net equals ma. This is the person on the elevator. They have weight. They have a normal force. So the normal force minus their weight equals ma. All I've done is filled in the forces for F net. And we want to know the scale reading, so we want the normal force. Normal force equals mg plus ma. So the normal force will equal, a person is standing on the scale, well, I didn't tell you their mass. Let's say it's a 50 kilogram person. So 50 kilograms times, I'm going to use 10 for g, so I don't have to use my calculator, and 50, and the acceleration is 2 meters per second squared, so 50 times 10 is 500. So that's their weight. That's what the scale would read if they were just sitting still. And 50 times 2 is 100. And so if they're accelerating upward at 2 meters per second squared, the scale, instead of reading 500 newtons, would actually read 600 newtons. All right, and the only change that's going to happen with this is sometimes there's no acceleration if you're moving at a constant velocity or not moving, and so ma would be 0, and the normal force would simply be the weight. Sometimes you're accelerating downward, and this term with the ma would be negative, and so the normal force would be your weight minus some quantity instead of plus some quantity. You have a whole elevator practice problem in the Newton's second law problems in your packet. And so I suggest you get that out and work every single part of it and check your answers. The solutions are online. And that's the end of this video. And thank you so much for your attention.